Okay, so let's move on to the next topic, which is linear dependence and independence. Very, very crucial idea in vector spaces, and we'll see it in the context of R2 first to make sure we understand it clearly, and then we'll extend so on. So we'll start by looking at a subcase of linear dependency, just to make sure our ideas are very clear and very simple. We will look at one vector v1, which we will consider being linear dependent or independent on another non-zero vector v2. Okay, so this is very important. I'm going to look at a subcase where this vector v2 is non-zero. Okay, to start with, we'll extend it soon enough. Okay, so a vector v1 is said to be linearly dependent on a non-zero vector v2 if v1 equals cv2. Okay, so this is a very simple condition, right? So you can easily see when do you say linearly dependent, you have v2 and another vector v1, when will I say v1 is linearly dependent? If I scale v2, I should get v1. So then there's linear dependence. If for non-zero v2, if there is no such c, if this is not a scaled version, then we will say v1 and v2 are linearly independent. Okay, so this definition is easy to picturize. You have v2 here. Okay, what are all the vectors that are linearly dependent on v2? It's the line through the origin, right, which is the span of v2. Okay, so that's the crucial definition. So all vectors in the span of v2 are linearly dependent on v2. Okay, so basically if any vector that is in the same direction as v2 or the opposite direction ends up being linearly dependent on v2. All other vectors that are not in the span of v2 are linearly independent of v2. Okay, basically different directions. Any two vectors that are in different directions are linearly independent in R2. If they are in the same or opposite direction, they are linearly dependent in R2. Okay, so notice how this definition comes about in a very simple way, but we have this non-zero vector v2 which is not very pleasing. Well, we will relax it soon enough, but for now this is a very nice thing to picture. Okay, so very easy definition, right? Linear dependency. Okay, so how do you define it when you have more than one vector? Again, we'll do the non-zero vector case first and then we'll extend to the zero case later on. Okay, if you have a set of non-zero vectors v1, v2, a vector v is said to be linearly dependent on these v1, v2 if v belongs to span of v1, v2. So notice how we extended from the previous definition. We had one vector, it was easy to see scaling. When you have two vectors, you allow for all linear combinations. If v belongs to the span of v1, v2, then we say v is linearly dependent on v1, v2. If v does not belong to the span of v1, v2, then v, v1 and v2 are said to be linearly independent. This is in the non-zero case. We'll generalize soon enough. Okay, so let's look at the two cases here. It may turn out that even though v1 and v2 are non-zero, v1 and v2 may be in the same direction. Okay, so like for instance, v1 may be in the span of v2 and you get in the same direction. If this is the case, then you go back to the old picture, right? So span of v1, v2 is nothing but the straight line through the origin. Then you know that if any line, if v is on the line, then it's linearly dependent. If it is not on the line, it's linearly independent. Sort of similar to before, v1 and v2 are in the same direction. The interesting case that happens is when v1 and v2 are in different directions. So v1 is not in the span of v2, v1 and v2 are in different directions. In this case, span of v1, v2 ends up being R2, which means what? All v, whatever v you pick, right? Once you have v1 and v2 in different directions, the span is entire R2. So any v you pick is linearly dependent on v1, v2. Okay, you can't have anything outside of the span. Okay, so simple, isn't it? So the whole picture of R2 is essentially becomes very, very simple when you think about it. So it's spanned by just two vectors which are in different directions. Okay, so I hope this is clear. This is linearly dependence when you have more than one vector, non-zero vectors in R2. Okay, so now we are going to generalize. Okay, this is the most general definition, and you'll see this goes back to the previous definitions. It ties up well with them. Okay, so linear dependence of a set of vectors. The vectors v1, v2 to vk are said to be linearly dependent if you have a linear combination of these vectors which becomes 0. Okay, a linear combination of these vectors should become 0. Now you should immediately tell me a valid linear combination is when I pick c1, c2, ck, all of them as zeros itself. If you put 0, 0, 0, 0 here, I will get 0, which means any vector is linearly dependent. Huh? No, that's not true. You're not allowed to do that. Okay, so what is the condition? c1, c2 to ck for some scalar c1 to ck with at least one of them non-zero. The all zero linear combination is not allowed. Okay, so you need a linear combination of v1 and vk to be 0, but a non-trivial linear combination where there's at least one of them non-zero. If this is true, then the vectors v1, v2, vk are said to be linearly dependent. hope this is clear. This is a very nice simple condition that we stated. You can go back and connect it to the previous one, right? So when V2 was non-zero, I said V1 should be in a scalar multiple of that. You get a linear combination to be 0. All of that is true. Okay, go back and check. Okay, for linear dependence, a non-trivial linear combination should be 0. This is the general definition. Okay. Linear independence, on the other hand, is the opposite of this. Vectors v1, vk are said to be linearly independent if whenever you have a linear combination which is 0, then c1 to ck is 0. Basically, only the trivial linear combination is 0 for linear independence. v1 to vk are linearly independent if the only way to linearly combine to get them 0, to get 0, is the trivial linear combination where everything is 0. Okay. No other non-trivial linear combination is 0. Okay. So, this is the general definition of linear dependence and linear independence. In the special cases that I introduced before, it was easy to picturize. Here it may be a little bit more abstract, but hopefully you see the way in which this definition comes about. Okay. So, let us fully write down all the possibilities. Okay. So, in R2 the possibilities are very simple. You may have one vector, you may have two vectors, you may have three or more vectors. When do you say one vector is linearly dependent? When can I get, if I have only one vector, how can a linear combination of that one vector become 0? A non-trivial linear combination becomes 0. The only way is if you have the origin. Okay. If you only have the origin, right, the one vector you have is the origin, then it's linearly dependent. It's sort of trivial. These one vector cases are really trivial, but still I want to labor the point to make sure the definition is clear. If you have only one vector, the origin is linearly dependent. Any other non-zero vector is linearly independent. Okay. If you have two vectors, if they are on the same line through the origin, these two vectors, both of them are on the same line through the origin, then they are linearly dependent, right? If they are in different directions, they are linearly independent. Okay. What will happen for three or more vectors? If you have three or more vectors, any three vectors you can pick and they will be linearly dependent. Okay. Think about that very carefully. You can pick any three vectors in R2, they will be linearly dependent. You cannot pick three vectors which are linearly independent. There is no possibility for three or more vectors to be linearly independent in R2. Okay. Think that through very carefully, right? So, if you have, just think about it, can you pick three vectors which are linearly independent in R2? If you have to pick two which are linearly independent, right, they will be in different directions. If they are in different directions, their span is the entire R2. Where will you go to pick the third one? You can't pick it from anywhere. Okay. So, this is a very easy way to quickly see in R2 how all these linear dependences and independences work. Okay, as we go to larger spaces, these things will be a little bit more difficult, but in R2 it's nice to do and we can nail them down very precisely. Okay. So, one can also do establish dependence independence by elimination very easily. Supposing you are given V1, V2 and assume both are non-zero, how do you establish linear independence or dependence? You write them as two rows and two columns, you eliminate. If one row is non-zero, they are linearly dependent. If two rows are non-zero, they are linearly independent. Okay, same as before, right? So, you can see how elimination ties in with dependence and independence. Okay. So, I hope you understood the linear dependence and independence structure in R2. Basically, two vectors in different directions are linearly independent, same direction dependent, and three vectors can never be linearly independent in R2. Okay. Thank you very much.